Hello, my name is Eugen Rabkin, and I will tell you today a few words about exciting research we are doing in my group. We are working in three related but somewhat different directions. First of all, we study mechanical properties of metal nanostructures such as nanoparticles and nanowires, which we manufacture by ourselves or with cooperation with colleagues from abroad. Actually, during the last several years, it became clear that mechanical properties of sub-micrometer size samples are very different from what is known from the studies, centuries-long studies of the bulk materials. And the laws governing the plasticity at the nanoscale are not clear yet. So this is one of our main research directions. Also, small metal samples are usually not stable kinetically, which means the driving forces for changes of their shape and macrostructure are so huge that already at moderate temperature they undergo significant changes. So we study the kinetics of those changes and the processes which control them, such as grain boundary diffusion, interface diffusion, and diffusion in the bulk. Also, we study ultrafine grain metal alloys and hybrid materials. Here on the picture, you can see an example of a hybrid material with a copper helix, which is embedded in aluminum conductor, and the whole sample underwent severe plastic deformation. So we also study the effects of deformation on microstructure. Just a few words what the students who graduate from our group doing in life. I just took a picture of our group some 5 years ago, and I want to show you that our students continue the academic path at the Technion, or work in Intel, or in technological startup companies, in defense industry, and one exchange student even works in German aerospace agency. So actually, working in academia has a great advantage, a great privilege. We are not supposed to produce a final product at the end of our studies, our research. Our main goal is to understand something, to understand it, to discover and to understand the new phenomenon. And to do that, we advanced along three main directions. First of all, the most important one is experimental study. In order to understand what we see in experiment, we develop simple analytical models which are based on diffusion equation, mass conservation laws, and thermodynamics of solid surfaces. The model should be, on the one hand, simple enough to be able to write it down in simple equation, but on the other hand, it should be sufficiently complex to be able to capture the new things that we see in the experiment. And we also perform atomistic computer simulations which occupy somewhat intermediate position between the experiment and theory. We build our crystal atom by atom in the computer, and we let the atoms interact according to the laws of classical mechanics, Newton motion law, and we see what is going on within the material. What you see here, for example, is a process of indentation of a single crystalline metal nanoparticle, which is indented by a hard punch. On this slide, I want to show you the result of one of our experiments on in situ studies of material mechanics. What you see here are the nanoparticles of molybdenum, which we compressed in situ in the scanning electron microscope using hard diamond punch. And you can see that the particle can be deformed elastically like a piece of rubber to incredible strains of like more than 10%, and then the particle just collapses in an instant manner. So we determine the strengths of our molybdenum particles, and we arrive at the very incredible values of like more than 40 gigapascal. Just for comparison, the strength of strongest commercially available steel is just like 2-3 gigapascal. So we exceeded the strengths of commercially available strong materials by an order of magnitude. Another example of the extraordinary strength that we achieve in our experiments on compression of nanoparticles is shown on this slide. You can see here the dependence of the particle strength normalized by the shear modulus of the material on the normalized dimension of the samples, particles or nanowires that we study. And you can see that we actually exceeded the strength of all other samples studied by other groups, firmly achieving the theoretical strength of molybdenum. And I would like to say that the sky is the limit for research in our group, also in the direct meaning, according to the direct meaning of those words. Probably some of you have heard about the science fiction concept of sky elevator. The idea is just to put a satellite on the geostationary orbit and connect this satellite with a cable to the Earth, so that you can attach the elevator to the cable and ship the satellites to the orbit without rockets, just moving the elevator back and forth. It's an amazing concept, and it actually can work, but there is only one obstacle for realization of this idea. There is no material which is strong enough to build the cable connecting the satellite with the Earth. With our experiments, with our particles and nanowires, we approach this specific strength limit, which probably in the future would allow building such space elevator. So if you are interested in doing research in our group, please contact me. Thank you.